Okay, g'day everyone. In this video we're going to be tackling this integral, which is the definite integral from 0 to pi over 2 of sine of x times by the natural log of tan of x. This can be approached as with many integrals in a variety of different ways, and this is actually going to be the first method I'm going to present, and then I'm also going to be uploading another video either today or within the next couple of days to show you an alternative approach. Okay, now whenever I'm dealing with a situation that involves trigonometric integrals, I quite often try, if I have the product of two functions, which is what we have here, sine of x and the natural log of tan of x, is there a way that I can actually get rid of having to use the trigonometric functions? Now, often this comes about through what they call a u substitution. Now, in its classic form here, or sorry, not classic, but the standard form as we have presented here, tan of x and sine of x are not directly related with an easy derivative. But there is actually ways in which we can take tan of x and represent it in terms of cos of x that allows us to do that. And so that's what we're going to do here. Now, in order to achieve that, we're going to have to go through some trigonometric identities and a few rearrangements, but it's fairly simple stuff, thankfully. Okay, so we start off with the standard identity of sine squared of x plus cos squared of x is equal to 1. Now, if I divide both sides by cos squared of x, which is what I've got within this step, I've got sine squared of x plus cos squared of x over cos squared of x is equal to, and then on this side, 1 over cos squared of x. So splitting up the fraction, we have sine squared of x over cos squared of x plus cos squared of x over cos squared of x is equal to, and remember 1 over cos squared of x is equal to sec squared of x. So therefore this means sine squared of x over cos squared of x is just equal to tan squared of x plus cos squared over cos squared is equal to 1, and then we've got sec squared of x. So you can see here we've started off with this identity, and now we've got something that combines tan and cos. Remember, sec is just 1 over cos. Okay, so if I want to make tan squared of x the object, obviously I just need to subtract the 1 onto this side. So I've got tan squared of x is equal to sec squared of x minus 1. Remember that sec squared of x is equal to 1 over cos squared minus 1, which is cos squared over cos squared, which equals 1 minus cos squared over cos squared. Now you'll see, obviously, I could have done this in a shorter number of steps. The reason why I went from here to the tan and the sec to the sec function is that I just wanted you to be aware, because this is such a common identity that is used in a wide variety of different mathematical applications, but I use it a lot when it comes to integration as well. So I just wanted to show you the complete picture there. Now, remember I said that I'm hoping to get everything in terms of cos of x. Right now it's cos squared of x. So my first thought is, well, can I do something to what I've got right now in order to put it into a form that just involves cos of x? And you see here, this essentially is taking the form of a squared minus b squared, where a is equal to 1 and b is equal to cos squared. And so as a result of that, we can use the, what is it referred to? The completing the squares. So a squared minus b squared is equal to a plus b times by a minus b. We have 1 minus cos squared. Now remember, 1 is just the same as 1 squared. So we have 1 squared minus cos squared. So here, using this formula here, we've got a is equal to 1, b is equal to cos, and so then we just apply to what we have within here, 1 plus cos of x times by 1 minus cos of x. So this expression for tan squared of x, in terms of the numerator, we can now not have to rely on cos squared. We can have it just in terms of cos of x, which is, remember, the goal is to get everything just in terms of cos of x. Okay, so therefore, tan squared of x, which is 1 minus cos squared of x over cos squared of x, which is what we had here, we now know we can replace this numerator with the expression that we derived here, and we have this. Okay, now there's still a couple of issues. Obviously, we've got this cos squared component here, and we've got that it's a tan squared component there. Now, here in the integral, we've got tan of x. So, obviously, one way I could go about it is going, well, I've got tan squared is equal to this. Why don't I just take the square root? And I could do that. The problem is it makes it a messy thing to deal with. So what we want to do is go, okay, we've got a natural logarithm here, so we've got a log function. Is there something, a log trick or a log rule that we can use in order to take a tan squared expression and use it to express a tan of x expression? And we can, thankfully. So, one of the very common fundamental log laws is log of a to the power of n is equal to n log of a. Now in our situation, we've got like a log of a situation, a being tan of x. So if I want log of a on its own, I just divide n onto this side, and I have log of a is equal to 1 over n times by ln of a to the power of n. And this holds for any value of n that is, well, obviously 0 would not apply, and there may be some issues with taking the limit as n approaches infinity, but certainly for any finite value that is not, 0, this will apply. So, we could use 2, 3, 4, 5, pi, e, whatever we want. It applies for all values of n. Here, obviously, because I've got tan squared, I'm going to use n is equal to 2. So therefore, ln of tan of x, just here with a being equal to tan of x, is equal to 1 over n, which is 1 over 2, ln of tan squared of x. So again, I've taken this component of the integrand and I've expressed it in terms of tan squared, which is great because that tan squared allows me to put it into the form of cos of x. At least for the most part, we still have this issue here. Thankfully, we will be able to resolve that simply. Okay, so therefore, my apologies, the natural log of tan of x, which is equal to 1/2 of ln of tan squared of x, which is what we just derived, is equal to 1/2, and we're going to replace the tan squared with the component that we just derived, 1 plus cos of x, 1 minus cos of x over cos squared of x, which is what we have here. Now, again, you may be looking at this and going, how is this better? You have taken just ln of tan of x and you've converted it into this horrible expression. Much, much more nastier to look at on the surface. Thankfully, though, with log laws, we can actually make the situation much easier. So we're going to use two log laws now. We have the log of a product of AB is equal to the log of A plus the log of B, and the log of A divided by B is equal to the log of A minus the log of B. So we're going to use this component for the two components on the numerator, and then we're going to use this rule for the component on the denominator. So therefore, ln of tan of x, which is equal to 1/2 ln, this expression here, is equal to 1/2, just remember the 1/2 is just a constant out the front. The ln of this plus the ln of this, we have the plus there because they're multiplied by each other, but then we have a minus here for the bottom component because it's the division, so minus ln of cos squared of x. So you can see we're getting closer and closer to just having expressions that are purely expressed in terms of cos. And most importantly too, that we don't have this really complicated form. We can actually, with the log laws, separate it out into much simpler expressions. The problem that we still have though is cos squared. I don't want cos squared, I want cos. So thankfully though, we can go back to this rule that we used before, which is the log of a to the power of n is n log of a. So we have cos to the power of 2, a to the power of 2, so it's just 2 ln of a. And so that's what we have in the next line here. We have 1/2, remember that's just the constant out the front. First two components remain unchanged, minus, and all I've done is taken the 2 here and brought it out the front, again, as per this rule here. Okay, in the final line, I have just pushed the constant through. So we've got 1/2 times by this, plus 1/2 times by this, plus 1/2 times by this. The 1/2 here cancels with the 2, and it just becomes a minus. So again, as much as it may seem odd that it looks like I've taken one function and converted it into 3, by doing that, and remember that the core goal and the motivation was I want it in the form of sine of x times by something with cos, so that I can then use a u substitution in order to get rid of the trigonometric functions entirely, so get rid of sine and cos. Okay, so let's plug it into our integral. I, which is equal to the integral from 0 to pi over 2 of sine of x ln of tan of x is equal to 0 to pi over 2 sine of x. We have found that the natural log of tan of x is equal to this expression, which is what we have here. And all I've done is I've just applied, my apologies, the linearity property of integrals. So I've just pushed this sine of x through, and then I've split them up into separate integrals. This is allowable as long as the functions are continuous, and these are proper integrals. There are situations with improper integrals where you are not allowed to do this. So for the first one, we've got sine of x times by ln of 1 plus cos of x, which is what we've got here. The 1/2, because it's a constant, we can take it out the front. So we move on to the second component, sine of x times by ln of 1 minus cos of x, which is what we have here. Again, the 1/2 is brought out the front. And then for the final one, it's just sine of x times by ln of cos of x. There's no constant to bring out the front. Well, the constant is -1. Okay. So the next step, as I said, this is what I wanted, even though I've taken a single integral and I've converted it into 3 integrals, I now have it in this form of sine cos. So I can then just use a very simple u sub in order to get rid of the sine and cos terms. So I'm going to let u is equal to cos of x. So if we have u is equal to cos of x, that means that du dx is equal to minus sine of x. So therefore, if we rearrange, dx is equal to minus du over sine of x. Now, because these are definite integrals, we also have to modify the bounds as well. So remember, we're making the transformation, u is equal to cos of x. So when x is equal to 0, we have u is equal to cos of 0, which is 1. And then for the upper bound, pi over 2, remember this is the same for all of them, we have x is equal to pi over 2, which means that u is equal to cos of x, or cos of pi over 2, which is equal to 0. So each of these bounds change from 0 to pi over 2 to 1 to 0. And for each of these integrals, dx gets replaced with minus du over sine of x, and cos of x is just replaced with u. So that's what we're going to do in our next step here. So this is the integral that we had before. Remember, as I said, let's just do this individually. All of the cos of x's become u's. So we can see it there, there, and there. Okay, the next component is our dx becomes minus du over sine of x, which is we see here, here, and here. And then the final component was that for each of the bounds, 0 to pi over 2, they become 1 and 0, which we see here, here, and here. Okay, so the next bit is, which is great, is we can see that for all 3 integrals, these sine of x cancel out. So they're gone, which is fantastic. So we've gotten rid of having to rely on trigonometric functions. We've now reduced it down to just logarithms. But we have this 1 to 0 situation, and you'll see that in this line, it's gone from 1 to 0 to 0 to 1. And the reason for that is this negative. So in case you are unaware, if you have an integram with a negative component, you can swap the bounds. So this negative changes it from 1 to 0 to 0 to 1. Now, because that negative exists in all 3, because it's the same transformation, that means that each of the 1s to 0s, in terms of the bounds, becomes 0 to 1. And so now we have an expression. Yes, we've got 3 integrals instead of 1, but we don't have both trigonometric and logarithmic functions, and we also don't have any intersection of the two. So we've simplified the intensity, for lack of a better word, of the integral that we're dealing with.